Welcome back. My name is Clayton. I'm one of the tutors at the Natural Sciences Tutoring Center here at Scottsdale Community College. This video is going to be about H-NMR, nuclear magnetic resonance. It's the third type of spectroscopy that you're responsible for in your Ochem class. I will be using a table from this textbook later in the video here. This is the Wade 6th edition organic chemistry textbook. Has a table of values for where you could expect to find chemical shifts for various, high proton environments. Nothing too crazy. Let's go ahead and jump right into it. First, we just want to talk about some general principles. Number one, the number of unique proton environments is equal to the number of different absorptions, or the different number of signals that you'll see on a spectra. Number two, the intensity of the signal is related to the number of protons that are in any given environment. So the higher or the stronger the signal, that is an indication that there are more protons that share that environment. And what we should also know is that these are relative to each other. Third, a greater chemical shift, which is usually measured in parts per million, ppm, corresponds to a proton that is closer to an electronegative atom or group, or closer to a stronger electronegative atom or group. So for instance, we're going to talk about one on our next here, carboxylic acid, very high electronegativity. You're going to expect something around a 10 to 12 ppm range. Something that is next to an alcohol, that's like 2 to 5 or 3 to 4, somewhere around it, somewhere in there. So that can help give you an indication of which functional group that proton environment is close to or closer to. Finally, the splitting of the signals. In any given signal, you might have multiple little peaks in there. And so the number of peaks is equal to the number of neighbors that proton has plus 1. And neighbors refers to protons on an adjacent carbon or on an adjacent atom. So if there are protons that are attached to the same atom, those are identical protons, not neighboring protons. All right, so let's just get a quick example so that we can kind of show how these rules work. This is propionic acid. It's a carboxylic acid. So what we can learn from this is kind of how I would break this down. I see 1, 2, 3 signals. So I know there are 3 unique proton environments. All right, excuse my handwriting. So that's the first thing we can learn from this. There's 3 signals, that's 3 environments. Now, if I look at how far this one is. This is 10 to 12. So if I go to this next page over here, right here, carboxylic acid has a range of 10 to 12 for your chemical shift. So I would expect this to be the this guy right there. That proton is represented by that peak. This peak only has one, or this signal only has one peak in it, so I know it has 0 neighbors. And so this one has 0 neighbors, which if we look at the adjacent atom to which this one is bonded to, there are no hydrogens bonded to this adjacent neighboring carbon atom. So that makes sense. So now let's look at this and this. So here, this has a higher chemical shift than this one does. So I would expect this to be closer to the carboxylic acid group. And this one, of course, is farther away. So that kind of gives us an indication of what we're looking at. So if I were to start drawing this, I'm going to use orange to draw it here. I know I have 3 environments and I have a carboxylic acid. So here I already have a COOH. So I have that. And now I know I have another C at least, because I have at least 2 more environments. So maybe there's something in between these. We'll have to look at that. Now, if I zoom in on this right here, this shows multiple peaks within this signal. So in this signal, we have like 1, 2, 3, 4 peaks, okay? So this is 4 peaks. If it has 4 peaks, that means it has 4 peaks. It has 3 neighbors, because the number of peaks equals the number of neighbors plus 1. So 3 plus 1 equals 4, and it must have 3 neighbors. Let's zoom in on this one here. We have 1, 2, 3. So this has 3 peaks. Therefore, it must have 2 neighbors. So at this point, I have a proton environment that has 3 neighbors and another proton environment that has 2 neighbors. Well, if I just draw the hydrogens on here right now, I already know that it's propionic acid. I can see here these protons have 3 neighbors, and these protons have 2 neighbors. So that matches. So let me erase a couple things real quick, just so you can get a look at this here. This pattern right here, that's characteristic of an ethyl group. So these patterns go together. Finally, let's look at the height of these peaks. That's there, that's there, that's there. That is the shortest, that's the tallest. So I would expect this proton environment to have the most protons in it. And in fact, this peak corresponds to that environment right there, where there are 3 hydrogens. This is the next tallest. Here we have 2 hydrogens. This is the shortest. There's only 1 hydrogen in that one. So that is how you can utilize these rules right here. That's what these mean. You can get information from your spectrum about the structure of your compound based on these rules. So if you're comfortable with these rules, then you will be able to do some of this, hopefully all of that. Moving on here, we have just a table of values. Just like in your IR spectrum, you had a table that had, alcohols 3,300, amines are like 33 to 35. Your CH, bonds are like 3,000 or maybe 3,300 if it's an alkyne. This is the same kind of thing. It's really important to just have an idea, a rough idea of what these, the chemical shifts look like, what the ppm is. We knew right away that this is going to be a carboxylic acid because that shift was so far over. Look, that's the only one. Carboxylic acid is the farthest one over. So if you have a general idea of where these shifts occur, then it's a lot easier to start predicting what the structure looks like. I would say one of the most important ones on here is going to be this guy right here. This is a proton bonded to a phenyl group, otherwise known as this right here. And so what that tells you is if you see something around like between 6 and 8-ish, then we have a benzene ring in here. That's a good piece of information. All right, so let's continue. Here we just want to predict the number of protons in, or proton environments, in these compounds. So all I'm going to do is identify the unique proton environments. So here we have 3 protons. All 3 of these protons are in the same environment. So we have 1 right there. Here's some protons. Here's more protons. We have all these protons. And actually, all of these protons are in the same environment. Why is that? It is because From this point, if I go there, there, and there, it's equivalent. From this point right here, that, and that is all the same. And so these proton environments are not unique to each other. So in this one, even though I have a ton of protons, it looks like they might be different, I only have 2 environments. All right, so let's move on to the next one. I have 3 protons on this guy. I got 2 right here. I have 1 right here. And if you're not comfortable reading line angle formulas, you're going to be in trouble. So if you're not there yet, get there, because you just don't have time to struggle with the line angle formula at this point in the game. So here, that is unique. There's nothing else. So those 3 are in the same environment. These 2 are in the same environment. There's nothing else that looks just like that. This guy is all by himself. He's bonded to that carbon. But then from this carbon, I can go that way or that way, and that's exactly the same. So these are all in the same environment. So let me put some circles here. So there's 1 environment, there's 2, there's 3, and there's 4. So this one has 4 environments. All right, let's do our last one here. So I have 2 hydrogens there, 2 there, 2 there, 2 there, 1 there, and 1 there. All right, so this one, a little bit different. Let me grab a red. All right, so basically, let's look at the easy ones first here. This carbon and that carbon right there. If I go around in this direction and this direction, it's the same as if I do it from this carbon right here. I can go around this direction or this direction. It's exactly the same. So actually, let me grab a few different colors here now. Okay, so this carbon, or sorry, that hydrogen and that hydrogen, they're in the same environment. These hydrogens are in the same environment, obviously. Now, if I look at this carbon, I can see it's the same. This is a symmetrical compound. So this carbon and this carbon, I can go this way, 1 away, I have this bromine, or 1, 2, 3 away, I have this bromine right here, right? So, and that's true for that and for that. So these guys, that and that is the same environment. And then finally, that's the same environment. So here we have 1, 2, 3, 4 unique environments on this one as well. So if there's symmetry within a compound, we would expect to see that the proton environments on different carbons are actually the same environment. So keep an eye out for that kind of symmetry. All right, so that's just determining the number of proton environments. So here I would expect 2 peaks or 2 signals. Here I would expect 4 signals and then 4 signals on a H-NMR spectrum. Here, the last 2, we're just going to look at splitting patterns now. So in this case, a couple things I want to bring to your attention. First, look at this guy. This is between 6 and 8. If we go back to our table here, 7.2 between 6 and 8, I already know that I have a benzene ring. So obviously we have this structure down here. But anytime you see something between 6 and 8, your brain should scream, benzene? Is that a benzene? Because most likely is, okay? So we have a benzene ring here, and you can see this is a little muddled in here, like how many signals are there? These are technically, if you get into the nitty-gritty, different from each other, but because this is non-polar generally right here, they're going to show all up in the same thing, and so that's why it looks like this, okay? Let me erase some things. This is becoming a little bit of a mess. So technically, if you're asked on a test, you know, there's one unique signal, 2, 3, 4, 5. We have 5 unique proton environments, but do they show up uniquely on our H-NMR? In this case, no, and that's why this is not a perfect thing, right? It's not like, oh, the rules say this, and so it's always this. You have to be able to kind of bend those rules a little bit because we live in a real world where things aren't perfect, right? And so, again, you can see that it looks like possibly we have multiple peaks in here somewhere. Yeah, but it's like impossible to read or whatever, right? This is really just indicative of an aromatic ring, okay? So that's one thing I just wanted to point out real quick. What I really want to draw your attention to, and well, if we look at the height of that, that's helpful as well. But anyway, what I really want to draw your attention to is this and this. We actually already talked about this pattern. Let me zoom in. Here we have 1, 2, 3, 4. Here we have 1, 2, 3. So if you see this pattern right here, you should be thinking that is an ethyl group because I have on this one I have 4 peaks, which means 3 neighbors. And on this one, I have 3 peaks, which means I have 2 neighbors. And okay, so 3 and 2, what does that look like? I'm going to draw some random R group. C, H, H, there's your 2 neighbors. C, H, 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 there's your 3 neighbors. What is that? That is an ethyl group. So anytime you see this pattern in there, you want to be thinking ethyl group. And sure enough, obviously, we have that right there. Let's look at another common splitting pattern. This is going to be this is just some ketone. And what I really want to point out is just a couple things. This, here, let me just bring this out. So it looks like this. H, there's like the rest of my R group. Then I have C, H, 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 and then again a C with an H, H, H. Now all these, right there and right there, there and there, those are all in the same environment. They're equivalent to each other. And you can see they even labeled them here, A and A. Those are HAs. And there's going to be 6 of them. So I would expect a pretty tall peak. In here, this is labeled C, if you can see that. That's this one right here. Let me circle that one with blue. So that is only 1. So look how short that is, first of all. But also, let's zoom in on this. 1, 2, 3, 4, 5, 6, 7 little peaks right there. What does that mean? It has 6 neighbors. And then this right here, 1, 2 peaks, that means it has 1 neighbor. So 6 neighbors, 1 neighbor. Well, that is right here. This one guy has 6 neighbors, and these 6 guys have 1 neighbor. So you can see that these peaks kind of interact with each other in those ways, right? And that identifies an isopropyl. So this, in conjunction with this, is an isopropyl group. Let's look at this guy right here, this one. This is 1 single peak. What does that tell us? That tells us that we have no neighbors. Okay, well, let's look back at our compound here now. No neighbors. Look at this guy right here. The adjacent carbon has no hydrogens bonded to it. So this has no neighbors. So that's why we only have 1 peak within that signal. All right, so those are just some common splitting patterns. Recognize your isopropyl, recognize your ethyl. The faster you can recognize those things, the easier your life becomes when you're trying to build an actual structure, okay? I think that will do it for this video. Thanks a lot. See ya.